Welcome to Spring LIB.
Once again, welcome to new problem. This time we have, I don't want to call it a space shuttle, but I want to call it a beam. It's a laser beam, so we're dealing with a laser beam. And assume that it starts from an optical station. So this is an optical station. And the optical station can happen to be in an Air Force base. We can have it in an Air Force. I don't know why I'm saying office, but this should be an Air Force base. And so what happens is the beam takes off. The beam takes off and goes in one direction, and it so happens to be going onto a shuttle. So it's going to collide with a space shuttle. I'm assuming this is a space shuttle, and so the beam leaves the optical station, goes all the way up until the space shuttle, and the distance that it covers is equivalent to 354 kilometers. That's the distance that it covers. This is the information that we're given in the problem. And if we assume this is the central max or the central maxima, there's going to be a diameter. Okay, there's going to be a diameter, and that diameter we're interested in is assume it's right here. This is the diameter we're dealing with. This is what we're interested in. At the shuttle, this is the shuttle. At the shuttle, the diameter happens to be 9.1 meters. So assume this is 9.1 meters. That's the diameter. And another piece of information that we're given is lambda, which is the wavelength, is 500 nanometers. That's our lambda. And our goal in this particular problem is to determine this opening right here. This opening in the optical station. We're looking for that gap, that diameter. What's the diameter right there? That's what we're looking for in this particular problem. This is our laser aperture. That's our laser aperture, and we're looking for the diameter of that. And this spreading that you're seeing of the light, that one happens because of diffraction. So the spreading happens because of diffraction. Just to summarize the pieces of information that we're given, we know that the distance between the optical station and the shuttle is 354 kilometers. And at the central max, we have a diameter of 9.1 meters as it reflects and collides with the shuttle, the laser. And we want to find the diameter of the laser aperture. That's what we're looking for, given that the wavelength is 500 just 500 nanometers. So those are the pieces of information that we're given. We're going to go ahead and assume that the distance covered from the shuttle up until the optical station is 354 kilometers. That's given, and the diameter of the linear separation is 9.1 meters. We're calling that linear separation diameter. 9.1 meters. The wavelength lambda is 9.1. Sorry, not 9.1, but the wavelength is 500 nanometers. That's the wavelength, 500 nanometers. The diameter of the laser aperture is given by D, and that's what we're looking for in this problem. The diameter contains twice the Rayleigh's angle, and because of that, we're going to say that 2 theta r, assuming that this is our theta r, 2 theta r is equivalent to 2 times 1.22 lambda over d. So you can see there's a relationship between that angle and this value right here. And so we can simplify for d through cross multiplication, multiplying both sides by d and dividing both sides by 2 theta r. And if we do simplify the problem, we're going to see something else happening in this particular problem. This is d equals to 2 times 1.22 lambda L over D. That's another way of seeing it. We don't even have to divide both sides by D because we're doing a different kind of replacement in this particular problem. And that replacement, as you can see, is connected to the small d. Is connected to the small d. That's the replacement we're doing. And the reason for that, the 2 pi over d is 2 theta r is also the same as d over L. So they're equivalent. 2 theta r is d over L. So it follows that, we could solve for theta r if we wanted to. If we could solve for that. But we can see that if 2 theta r is d over L and 2 theta r is 1.22 lambda over d, then we can say d over L is 1.22 lambda over d. And that makes our life easier because we can go ahead and multiply both sides by d, and then multiply both sides by L over d like that. We're simplifying this problem. These two cancel out, these two cancel out, those cancel out. And now we're solving for d is 1.22 times lambda L all over d. And this will help us simplify the problem. So we're saying d equals to 2 times 1.22 times 500 nanometers. 500 nanometers. We can change that to meters by saying this is times 1 meter over 10 to the 9 meters, and then multiply that by the kilometers, which is 354 times 10 to the 3 meters. This is in kilometers, so we're transforming that into 10 to the 3 meters per kilometer. Then we divide the whole thing by d, and d happens to be 9.1 meters. So when we simplify that problem, we get to see that d is 0.047 meters, or we could say d is equivalent to not just 0.047, but change it into centimeters, so 4.7 centimeters. So once again, our goal was to find the aperture, we wanted to find this aperture right here. It's a small one, and it's on the shuttle, this one right here, the diameter of the aperture. And it takes out the beam of light, which goes all the way up until the shuttle, and it's reflected back. The diameter that we're dealing with is, for the central maxima, is 9.1 meters, with the distance of 354 kilometers. We're using Rayleigh's angle to simplify this particular problem. So equivalences are happening here. First one is 2 pi, or rather 2 theta r is d over L. D is the distance, or the diameter, and L is the distance. So D is this diameter, capital D is this diameter right here, and L is that distance, and this is our small d, the diameter of the laser beam. So and this is our lambda. Pieces of information were given. So we're going to go ahead and simplify for D, and we end up with 4.7. So hope you enjoyed the problem. Feel free to send any questions or comments, and have a wonderful day.